Come on. Let's talk about
spheres,
let's talk about you and me. Let's talk about all the good things and the bad things that may be. Let's talk about
spheres,
let's talk about
spheres.
So, let's talk about spheres. Many people think that spheres are some sort of complex entity that would only be discussed in a geometry class. In reality, spheres are all around us. Let's take a minute and talk about some common examples of spheres that we might encounter in our everyday lives. Spheres are very common in sports. Some examples are a basketball, a tennis ball, and a soccer ball. Spheres can also be found around the house. For example, this trendy lampshade, a magic 8 ball, or cat toys. Spheres on a larger scale may also be found in outer space, like Earth, the Sun, and the Moon. So now that we've considered some spheres that might be encountered in our everyday lives, you may be wondering how these spheres relate to the spheres we talk about in geometry class. Let's talk about some different properties of spheres. Sphere, a round, solid, three-dimensional figure or its surface with every point on its surface equidistant from its center. We recall that three-dimensional means that a figure has length, width, and height, and equidistant means that all the distances are equal. Let's consider an orange as our example of a sphere. You could take a piece of string and wrap it around the middle of the orange to find a measurement of the orange. This measure that you would find is called the circumference of the orange for the exact spot that you wrapped the string around the orange. If you were to cut the orange through the place where you wrapped the string around the orange, you would be able to see a cross-section of the orange. Here, we see what this cross-section would look like. The cross-section is a two-dimensional circle at the very spot where we sliced the orange. We can see that the circumference we found using the string is equal to the perimeter of the circular cross-section. Now we mark the center point of the circle. In this picture, we see the radius, which is the distance from the center of the circle to the perimeter of the circle. The radius is the same length, no matter which point of the perimeter you are measuring to. We can also see the diameter, which is the length of the line segment that starts at one point on the perimeter, goes through the center of the circle, and goes to the point on the perimeter directly across from the initial point. We can see that this length is made up of two lengths of a radii, so we can say that the measure of the diameter equals 2 times the radius. As we measure these distances, we notice that there is a relationship between the measures of the circumference of a circle and its diameter. The ratio between the two is always the same. This ratio is called pi. We use it to form the equation for the circumference of a circle. The equation is circumference equals pi times diameter, or, since we know that the diameter is equal to 2 times the radius, circumference equals 2 times pi times the radius. Naturally, we begin to wonder about the area of this cross-section. To find an approximation of the area of a circle, we use a method passed down to us from our pal Archimedes. Using this method, we start by drawing regular polygons around the circle or circumscribing it. We use regular polygons because we are familiar with finding the area of these figures. With these measures, we get an estimate close to the area of the circle, but slightly larger. Then, we draw regular polygons on the inside of the circle, or inscribe it. With these measures, we get an estimate close to the area of the circle, but slightly smaller. These measurements that we find are the upper and lower bounds of what the area of the circle is. We can see that polygons with a larger number of sides will give us a closer estimate to the actual area of the circle. Now, we use another method to compare Archimedes' method to. We look at a square. We know that if a square has a side length of s, then the area of the square is s squared. We begin to experiment with how we might use the information we already know to calculate the area of the circle. Imagine we have 4 squares, each having a side length r, which is the same length as the radius of our circle. We can see that the total area of these 4 squares would be 4r squared, and their area is larger than that of our circle. Here, we can compare the area of 2 of those squares with side length r to the area of our circle. The total area of these 2 squares would be 2r squared. Though one of the squares extends outside the perimeter of the circle, we can see that this is less area than the area of the circle that is not covered by the squares, so we know that the area of the circle is larger than 2r squared. Here, we experiment with 3 squares with side length r. The total area of these squares would be 3r squared. It looks as though the area of the squares that extends outside the perimeter of the circle is less than the area of the circle left uncovered by the squares, but it is difficult to tell. As we explore more with the areas we found using Archimedes' method and by layering squares with side lengths equal to the radius of our circle, we find another relationship. This relationship is between the area of the circle and its radius squared. We discover that the ratio is slightly more than 3. In fact, the ratio is the same as the ratio we encountered earlier between circumference and diameter. It is pi. With this, we find our formula for the area of a circle. Area equals pi times radius squared. That wraps up this week's discussion about spheres. Tune in next week when we talk about volume.